In recent years, we have had plenty of reasons to worry about virus invasions, right from the flu season to the Ebola epidemic to the use of viruses as agents of bioterrorism. The first step of virus infection is binding to the endothelial glycocalyx. My name is Ramya Kumar and I'm a PhD student at the University of Michigan where I work at the Lahan lab. I will be telling you about the use of polymer brush interfaces to model the interactions of viruses with the endothelial glycocalyx. Now, what is the glycocalyx and why should we even study it? Glyco means sugar and calyx means shell. The glycocalyx is a carbohydrate-rich layer that sheaths our endothelium. It acts as a first line of defense against virus invasions, but very little is understood about how this actually happens. If we look at the structure of the glycocalyx, we will notice that it is composed of oligosaccharide chains which are organized in a brush structure. These oligosaccharide chains can either expose or shield receptor groups on the cell surface, thereby determining whether a binding event occurs or not. Therefore, the glycocalyx acts as a molecular sieve and gets to decide what enters the cell and what stays out of the cell. The functionality and specificity of this molecular sieve depends not only on the size and charge of the approaching species, but also on the conformation of the oligosaccharide chains, more specifically, the thickness and the density of the oligosaccharide brush. It is also interesting to note that the glycocalyx has a strongly negative charge at physiological pH, and this greatly contributes to its anti-adhesive character. But what about viruses? What is the charge of a typical virus? Literature reports that most viruses have isoelectric points in the pH range of 3.5 to 7, which means that they are likely to be negatively charged at physiological pH. Now you may wonder, why doesn't the virus be repelled by the glycocalyx then? So even though the glycocalyx has a net negative charge, it may still possess islands of positive charge to which the virus may bind. The initial interactions of the virus with our cell is often electrostatic, and these positive islands of charge can act as catch holes from which the virus can recruit more specific receptors and eventually enter the cell. We will use this knowledge to guide our surface design. Our surface is composed of two parts. The base layer is a copolymer synthesized using chemical vapor deposition copolymerization of two paracyclophane-based monomers. One monomer contains an ionizable amine moiety and the other monomer contains a polymerization initiator. The aminomethyl group can acquire a positive charge upon protonation and act as an affinity site for viral species. The ester bromide group is used to initiate atom transfer radical polymerization. It serves as an initiation site for glycopolymer brushes, and glycopolymer brushes can be grafted with controllable chain length distribution and brush density. In our initial work, we used sorbitol methacrylate, but we are currently working on polymer brushes incorporating glucose, galactose, and mannose in their bioactive forms. By developing a synthetic mimic of the glycocalyx, we hope to identify key physicochemical parameters that shape the interactions of viruses with this critical interface. Thank you for listening.